Hey, Rexha. Hi, Teresa. Okay. Left off yesterday at um, page 454 on the notes. So yeah, I'll go over the phase changes, what they look like, what they're called. It's very easy stuff, but then we'll expand from there. So if you look at a gas turning into a liquid and also a solid, there are changes that go through all those different layers. And we learned in grade 9 that each one has a name. This is called deposition, although it's also been called sublimation in both directions. Sublimation if you go from a solid to a gas. If you go from a liquid to a gas, it's evaporation, which occurs at the boiling point. And if you go from a gas to a liquid, it's called condensation. You go from a solid to a liquid, it's called melting or fusion. I want to sound more scientific. And freezing. Keep going the other way. And in each case, as we learned in chapter 5, there's an energy cost involved depending on how much material you have. And typically we measure it on the basis of a mole of substance. So there's a molar heat of fusion, a molar heat of freezing, and by the way, it has the same amount. It's the same amount. The only difference is the sign is changed because when you're melting a solid to turn it into a liquid, you have to add heat energy. When a liquid turns into a solid, it gives off the same amount of energy as went into doing the opposite. Okay? And we'll see, we're going to explore a little bit of that in a calculation later. The book also mentions two types of forces, cohesive and adhesive. Let me just show you what that looks like. Cohesive force is the intermolecular forces that bind similar molecules to one another. Adhesive forces are intermolecular forces that bind a substance to a surface. And if you look closely at a meniscus, usually when you, if you have, say, a burette, which is a long, narrow cylinder of glass, you'll notice that the liquid meniscus has a bowed shape. If you did the same with the meniscus of mercury, you would notice it has the opposite shape. Why does that happen? Well, in the case of the water meniscus, the water has a greater attraction for the glass than it does for other water molecules. So it climbs up. Hi, Rebecca. So it climbs up the glass. In the case of a mercury meniscus, the mercury has a greater attraction for self than it does for the glass. So the meniscus makes a bowed shape with the bulge in the middle. So this would be a mercury meniscus. This would be a water meniscus. And the explanation is, first of all, the shape of the meniscus discloses which of the two forces is greater, cohesive or adhesive. Cohesive force is greater in a water meniscus. Sorry, wait a second. No, water climbs up the glass, so the greater force is the adhesive force. Water meniscus has a stronger adhesive water attaches to glass better than other H2O molecules. And in the case of mercury, mercury meniscus discloses a greater cohesive force. Mercury is more attracted to self than glass. Hope you can read that. You better watch it on TV, or I don't know, you better have good eyesight. I can't get you really much closer than that. Getting back to finishing the topic of phase changes. With phase changes, if you were to observe a temperature versus time graph, you would see that the graph goes flat every time there's a phase change. So let's say you're warming up some water. The water keeps warming up. You'll see the slope of the graph going up. And then as soon as the water starts to boil, it'll flatten out. And it'll go straight, it'll stay at that same temperature until all the water boils away and turns into steam. Then the steam itself will start to warm up, so again the temperature will start to climb. So why does the graph flatten out when there's a phase change? Well, the reason is they call that latent energy. Energy is still being added to the system, but what's happening is you're breaking apart the hydrogen bonds that are holding the water molecules together so they can volatilize. So the energy is being absorbed by the molecules as they break free from the surface. Our body exploits this concept to cool us down. We sweat, which gives us the capacity to shed excess body heat. That's probably why although we are not particularly good runners in the animal kingdom, we can hunt other larger animals that don't have the capacity to sweat. So if you're chasing a buffalo in 90-degree heat in the desert, you would eventually win the race, because the buffalo weighs over 1,000 pounds. A human being only weighs about 180 pounds. So as long as you keep a slow pace of running, eventually the larger animal will get overheated, will have to stop running, and then you can catch up to him and kill it to feed your village. So and that's because we can sweat and larger animals don't sweat. They have fur and they pant to try to lose extra heat. They'll stay still for the hot hours of the day to avoid overheating themselves, but their biochemistry is different than ours. They don't have the same mechanism for disposing of heat. You'll see how dogs pant. Dogs don't sweat, they pant. They just hang their tongue out of their mouth and they breathe quickly in and out, and that helps evaporate saliva from their tongue, and that's their heat losing mechanism, which is why dogs should never be locked in a car in the summertime, because their panting mechanism actually doesn't help that much if the car gets really humid and in an enclosed space. The system doesn't work well. Plus, it's a small area to lose heat from a large volume body. So we probably have the most efficient heat voiding system in the animal kingdom. That gives us a decided advantage, although we're weaker everywhere else. Anyway, getting off topic here. Practice example on page 457. It shows you're asked what is the enthalpy change during the process in which 100 grams of water at 50 degrees Celsius is cooled to ice at negative 30 degrees Celsius. Hi, Eldinho. Use the specific heat and enthalpies for phase changes given in sample exercise 11.4. So let me just write the necessary ones down. We're dealing with water at 50 degrees Celsius, so we don't care about the boiling point. The only phase change we're going to go through in this problem is as we go down to 0, the water is going to turn to ice, so it's going to freeze. And we care about the cooling of liquid water, the phase change of liquid water to solid water, and then we care about the specific heat capacity of ice. So we only are interested in 3 of the numbers. So let's do that. We'll write them down. It'll help us solve the problem. So the specific heat of water in the liquid state is 4.18 joules per gram degree Celsius temperature change. The specific heat of fusion called delta H, freezing, let's say, no, not fusion, but freezing because we're going the other way, is equal to, keep forgetting I'm blind, ice, water, okay, ice is 2.09 joules per gram degree Celsius, and then you want the specific heat of ice. So C for H2O solid, it's not 4.18, it's 2.0. Okay, no, sorry, ice is 2.09 joules per gram degree Celsius. This is something else. Let me see. Fusion is 6.01 kilojoules. Ooh, kilojoules per mole, no less. Gotta watch those units, even if you're a chemistry teacher. Okay, good. So, maybe especially if you're a chemistry teacher. So we're taking water from, okay, we got 100 grams of water, and we're going from 50 degrees Celsius all the way to negative 30 degrees Celsius. How much energy is released? That's what the question is asking. Okay, so we'll break it into the 3 steps. We're cooling the liquid water, you're freezing the water, and then you're going to cool the ice. So 3-step calculation, add up all the results. Final result is how much energy. So Q equals MC delta T. That's the cooling of the water from 50 degrees Celsius to negative 30 degrees Celsius. And you get 100 grams of water times 4.18 joules per gram degree Celsius. Temperature change is 50 because you're going from 50 to 0. You know what? If the truth be told, even within one liquid, the C value is not a constant. So if you really want to do this accurately, you have to use calculus. But let's not go there. So you get negative 20,900 joules. So of course it's exothermic, right? The water's cooling down, it's giving off heat. It's exothermic. Then the next step is forming ice. So I have to erase all this. You can always pause it later. Show must go on. So Q equals MC. In this case, fusion. And you get 100 grams of ice. And the molar mass of water is 18.01528 grams per mole. So that means you've calculated how many moles of water you have there because our heat of fusion is given per mole. And it's 6.01 kilojoules per 1 mole. Be careful about that. One was joules, the other was kilojoules. If you don't notice, you'll end up getting the wrong answer. So multiply that by 1,000 joules per 1 kilojoule. And the amount of energy released when you freeze 100 grams of water is 33,360.56947 joules. Remember, fusion in reverse is freezing. Therefore, this is exothermic again. And the last bit is you're cooling the ice. And you're going to use Q is equal to MC delta T for that one. From 0 to negative 30 degrees Celsius. So you're going to say 100 grams of ice times the specific heat of ice, which is 2.09 joules per gram degree Celsius, times a 30-degree temperature change. Don't worry too much about the sign, we'll put it in later. We know it's exothermic. So the end result is negative 6,270 joules. And this is all cooling the ice. Sometimes students have trouble understanding the notion that ice can be cooled. As long as something is above negative 273 Celsius, it can be cooled, right? The absolute zero is at minus 273. So if you're warmer than minus 273, you still have heat. Now, if anything is, if I touch ice, obviously it's going to feel cold to me. It feels like, well, how can you have heat in the ice? Well, you still have heat in the ice. You can still extract heat from the ice. In fact, if we ever, let's say we ever go to a distant planet, obviously we can't land on Saturn or Jupiter because they're gas giants, but we'll be able to land on their moons. If we ever set up an outpost on one of those types of planets, it's 100 grams, 100.0. If we ever set up an outpost on one of those moons, we'll be able to heat up the outpost using the ice on the surface of the planet. If we have an appropriate gas exchanger, but it will obviously have to be some substance that remains a liquid at cryogenic temperatures, but you could theoretically extract heat even from very cold substances, provided you can cycle it through a compressor and by compression cause its temperature to go up. So the thing would have to be a gas even at very low temperatures, and then you would have to compress it, turn it into a liquid, which would cause it to warm up, and then the excess heat could be shed outside the surface, and then when you bring it back inside to the building, you would usually heat inside the building, you'd warm up the building with the compressed gas, and then the gas would go back to pick up more heat by expanding. That's how a refrigerating system works. You're alternately expanding and allowing a liquid to turn back into a gas in different places in the refrigerator. When the liquid is inside the refrigerator, it's expanding to cause a temperature drop. When you bring it outside the refrigerator in the coils, it's compressed to warm up the gas and shed the heat outside of the refrigerator. So it's a heat pump. The refrigerator is a heat pump, so it's taking the heat energy from the inside of the fridge and putting it to the outside of the fridge. we're not finished yet. We have to add up all three sections. So we had, for our total, we get negative 20,900 plus negative 33,360.59569, sorry, 407, and negative 6,270. I'll just cut to the chase. It comes out to 60.5 kilojoules. That's how much energy it takes to cool 100 grams of water, liquid water, down to minus 30 as a solid block of ice. Right, so you have to account for each one of the phase changes. So the whole process of cooling water from liquid to solid and then cooling the solid comprises one phase change, the cooling of a liquid and of a solid. Altogether, the total amount of energy released is 60.5 kilojoules. You'll notice that by far the biggest energy expenditure occurs when the water freezes. Surprisingly, because there was a 50-degree change, right? I would have thought the 50-degree change with water would have had a bigger effect, but no, the freezing of the water actually had a bigger effect. One other interesting thing I wanted to relate to you is the idea of critical temperature and pressure. Every gas reaches a temperature at which you can no longer liquefy it, no matter how much pressure you put on it. And that is a matter of interest to scientists because if you surpass the critical temperature of a large amount of liquid, it creates the possibility of an explosion, as they found out all throughout the 19th century when they had steam engines. Sometimes they would have steam engines doing races, and of course the engineers would block the safety valves to try to raise the boiler pressure so it could go faster. Well, every so often they got a little too carried away and they put it in the red line, and it didn't always work out. And if you get a boiler explosion, the expansion of the hot liquid into the gas creates lethality on a couple of levels. First of all, you get shrapnel because the liquid suddenly flashes into gas, so its volume increases massively. And on top of that, it produces very hot steam because it's superheated liquid, so the energy's still there. Even though you've gone through a sudden phase change, there's still a lot of heat there from the fact that the liquid was superheated. So it would tend to burn everything for several meters around. Anyway, at the critical temperature of a gas, it is no longer possible to liquefy the gas, no matter what the pressure is used. And at the critical pressure, it is the pressure required to bring about gas liquefaction at the critical temperature. Don't worry, I'm going to show you my notes after. You can copy them whenever you have a moment. For example, at a temperature of 304 Kelvin, a pressure of 73 atmospheres is necessary to liquefy carbon dioxide. This is actually a matter of importance to the food industry because they use carbon dioxide as an extraction liquid. Carbon dioxide is a non-polar solvent because it's a linear molecule. And so if, say, for example, you want to extract all the caffeine out of coffee beans, you use supercritical carbon dioxide. It's been pressurized, so it turns into a liquid, and it acts like a solvent. It removes all the caffeine, and then they can easily let it regasify, leaving behind caffeine crystals, which are easily extracted and done so in a pure way without affecting the taste of the coffee beans, as it turns out. Why is this useful? Well, you can determine the heat of vaporization of any gas by plotting a graph of the vapor pressure. First of all, what is vapor pressure? Let me just give you a little definition. So, vapor pressure, whenever a liquid is sitting in a container, the molecules at the surface of the container have thermal energy. They have kinetic energy. They're dancing around. Occasionally, one of them gets hit from below because one of the molecules on the average has a little more energy, because they're not all at exactly the same energy. They have a distribution of energies. And once in a while, one of the higher energy molecules hits from below and knocks one of the molecules on the surface of the liquid out into the air, and it doesn't come back. That's called evaporation. Okay? So because there's a distribution of energies of the molecules, some of the molecules actually get enough energy on the average to get kicked off the surface of the liquid. Now, if you were to put a lid over the surface of the liquid, you'd have an airspace between the surface of the liquid and the rest of the container. So what happens is those water molecules, say it's water that you're talking about, get kicked out, and they start building up a certain amount of water molecules flying around on the inside of the container. When you reach a certain amount of water molecules, some of them will start actually falling back in and getting stuck on the surface of the liquid. So when the rate of water molecules going up and the rate of water molecules coming back down is the same, you have an equilibrium, and the pressure exerted by the gas above that liquid is what we call the vapor pressure. Okay, so vapor pressure is liquids have some gas phase molecules above the surface of the liquid. This is on page 460, you'll see it on my notes. At every temperature, liquids achieve a vapor pressure over the surface of the liquid. And of course, each liquid has its own vapor pressure. Liquids that are more volatile have a higher vapor pressure. That's the definition. If you were to, if you look at molecules that have higher intermolecular forces, they tend to have lower vapor pressure because the molecules are more cohesive, they stick together. So if you were to compare carbon tetrachloride with carbon tetrabromide, because carbon tetrabromide has bigger bromine atoms, their London dispersion forces are better than the London dispersion forces of the chlorine atoms, so they're able to stick together a bit better. So the vapor pressure of carbon tetrabromide is lower than the vapor pressure of carbon tetrachloride. Same with boiling points. By the way, definition of a boiling point. Is the temperature at which the vapor pressure of the liquid equals atmospheric pressure. Obviously, we use 1 atmosphere. So water boils at 100 degrees Celsius if it's at sea level with 1 atmosphere of pressure. If you go to the top of Mount Everest, where the air pressure is 1/3 of what it is at sea level, the water will boil at something like 70 degrees Celsius. So it'll take you like 20 minutes to get a hard-boiled egg if you try to cook it on the top of Mount Everest, right? Because the water's boiling at 70s. It can take that much longer to cook your food. Then there's a chart on page 461 where by looking at the chart and extrapolating, you can tell what the vapor pressure of ethanol is at, what's the question asking? At 60 degrees Celsius. So if you extrapolate on the chart, you'll see that at a temperature of 60 degrees Celsius, ethyl alcohol has a vapor pressure of around 320, 340 torr. Okay? That's why, you know, when you fill your, say you go fill your boat with gas, one of the dangers with high vapor liquids that have a high vapor pressure is if you're not careful, the vapors can spill out of the gas tank. They go to a low-lying area in your boat, and then if you're unlucky enough to have a spark in the course of fueling, you can cause an explosion in your boat. So they always say to ventilate well when you're fueling up. How much time? We already used up half an hour. Time flies. Okay, one of the mathematical treatments of vapor pressure is called the Clausius-Clapeyron equation. Clausius-Clapeyron, I don't know how to pronounce it. It occurs on page 462 of your text. Okay, if you plot the law of vapor pressure, what's the unit? They don't give one. Versus the reciprocal of the absolute temperature in Kelvin, you're going to get a line with a negative slope, and the line will have a slope of negative delta H vaporization over R, so that delta H of vaporization will equal the slope, the negative slope, times the value of R, whatever units you happen to be using. The book also makes mention of what are called phase diagrams. This is all chapter 11. And in phase diagram, you make a two-dimensional graph of the liquid phase, the solid phase, and the gas phase of a substance. And on one side of the graph, you'll have pressure, and the other, you'll have temperature. So in a phase diagram, it's a totally different subject, okay? I've changed subject now. I've gone from talking about vapor pressure to now phase diagrams. It's all part of chapter 11. It's a graphical way to summarize the conditions under which equilibria exist between different states of matter. So you typically have a graph that looks like this. Pressure on the left versus temperature. And it'll create a diagram that looks something like this, where this will be solid, this will be the liquid, and this will be a gas. So typically when you increase the temperature on a solid, it'll stay solid, but if you keep on increasing the temperature, eventually the liquid melts. And you can keep on warming the liquid, and eventually the liquid will also turn into a gas. So these lines represent where the phase changes take place based on pressure, because increasing the pressure on something can prevent it from going through a phase change. This is something that they've theorized, for example, at the center of the Earth. As we all know, or at least believe, I don't know if it's true because nobody's ever been able to drill to the center of the Earth, but scientists theorize that the deeper you go into the Earth, the hotter it gets. But contrary to what you might think, the center of the Earth is not liquid. It's actually believed to have a solid iron core. Why? Because as you go deeper into the Earth, the pressure also increases. So it actually, even though the temperature keeps climbing and you would expect the iron core to become liquid, the high pressure forces it to stay in a solid state. So scientists come to this conclusion on the basis of diagrams like that, where they predict the behavior of solids on the basis of thermodynamic quantities that they've calculated. There's a particularly interesting point where all three phases meet, where both solid, liquid, and gas can coexist, and that's not the only point where all three phases coexist. It's called the triple point, and every substance has one. The triple point of water, for instance, occurs at 0.0098 degrees Celsius and 4.58 torr. Seems to me they should have defined 0 with that, but I guess they in fact did that, but maybe their methods were not as accurate as modern methods, and that's why it's shifted up to 0.0098. Practice example on page 464 shows you how to use a phase diagram. So it says, using figure 1127, describe what happens when the following changes are made in a CO2 sample initially at 1 atmosphere and negative 60 degrees Celsius. A, pressure increases at constant temperature to 60 atmospheres. Well, if you take gaseous carbon dioxide and increase the pressure on it, it can turn into a solid. And that's what the phase diagram corroborates on the top of page 464. And the second question, it says, if temperature increases from minus 60 to minus 20 at constant 60 atmosphere pressure, what happens? Well, your solid carbon dioxide will turn into a liquid, even though it's under pressure. All right, I'm going to, it's already 36 minutes. I'm going to stop it there because I want to do solids tomorrow. You can read ahead. I'll show you the notes I've written up to now, basically, just to top up. So I think I stopped here yesterday. I showed you page 5 notes, and there's the bottom of the page. Page 6 notes. There's the bottom of page 6. Hope you can read it. Page 7, top of the page. And page 8. Sorry, bottom of page 7. That was the bottom of page 7. Then top of page 8. This is stuff that's coming up. Then bottom of page 8. Top of page 9. Bottom of page 9. Top of page 10. Bottom of page 10. And I'm starting page 11 there. All right. So read into chapter 11, and I'll see you tomorrow.